It's been a real career goal of mine to share something that I thought was cool that I worked on in the community. So I'm really glad to be here and hope you all find it interesting. And thank you so much to Women Who Code for this opportunity and for all of you for coming. This talk is aimed for all people who are interested in applying machine learning for real products. And I hope to share tips and tricks on rapidly iterating on ideas to create a product that solves a real world problem, as well as using bits and pieces of technology adapted from research. And yeah, I'll be taking questions at the end. So I look forward to all your questions. Great. So this GIF that you can see is to just give an idea of what we built. This is a demo game that's inside of that we built with using Unity, and the player that's playing and avoiding obstacles and shooting, that's an agent that we trained on around 10 minutes of gameplay, navigation, and shooting. So basically, we started our service using our open source project and started the game, and then trained the AI, and now this is a video from it running. And you can download our open source project linked at the end of the slides to play around on your own as well, so you can replicate this. Okay, so I'll introduce a little bit more about myself, although we got a little bit of that as well. I started programming probably when I was in middle school, if you count HTML on like Neopets and other platforms. I don't know if people have played Neopets here, but serious coding started in college after playing a game called Portal. And that game was really cool. And I was like, wow, I wish I could make something like that and influence people's lives in a positive way. And that's why I started coding games. And then I graduated UC Berkeley with a degree in computer science and economics in 2015. Shortly after, joined a mobile gaming company called Zynga, worked on game titles such as Words with Friends, Dawn of Titans, as well as made SDKs and tools for supporting those games. And I joined YouTube Trust and Safety as a full stack engineer in 2018, and then joined Google Research as the 5th engineer to work on this synthetic players project, which is what I'm going to be talking about today. And the team was like a startup within Google, and I was brought on to productionalize a service for early access partners, which were external gaming companies, so game companies all over the world, and collaborate with those game companies and improve the AI quality for that service. And we were able to wrap up the project in July 2021, and by publishing a blog post and an open source project on GitHub. And now I currently work on, as it was said, NLU, so natural language understanding and AI quality team at Google Cloud Dialogflow, where I build conversational agents. Cool. And yeah, in my free time, I like to participate in game jams where I make small games and play other people's game. And I don't just play indie games. I also play, big games released by big companies. So first things first, for all research to market project ideas, there needs to be some explanation on why machine learning is how you solve a specific problem in today's world. And thank you, Sapphire. First, let me give you an idea of why we thought working on a machine learning service for game developers was a good idea. Well, game development is bigger and more accessible than ever. With free-to-use game engines and assets, technological advancements such as procedural generations for levels, indie-friendly publishers, and a large audience of gamers on various devices. And game developers around the world are generating enormous game experiences that players explore through hundreds of hours of play on various devices. So to deliver the experience, what do game developers do? In addition to making the games must be tested before they are released to the world to iron out any bugs before they are found by players. And those bugs are found via a manual QA process where a large number of people just simply play the game to find bugs. And that gets more complicated as the game has more elements, like what about multiplayer? A vast world with multiple combinations of environmental factors that shape the gameplay, complex skill and item trees, different OSs. And this QA is a bottleneck in the process, which is unable to scale with the complexity of these modern games. And it leads to delayed launches, lower quality products, and they're just huge money sinks. So our team at Google Research had a goal to create a product that directly addresses this imbalance by creating a service that allows game developers to train an AI that can play and test their games at scale quickly and easily. And while there are tons of research in AI that orients itself around playing video games, this problem came with requirements that were very different from ones researchers face. And that's what I like to focus on today. So yeah, here are some restrictions that we faced. We had to restrict where the games are run. So game companies have strict requirements on where their binaries are run, while machine learning researchers often run their target game and machine learning code in the same data center. We had to build a service, and oftentimes researchers don't have to build services. And we had to build the service for a specific audience, which was game developers who often don't have experience working with machine learning and expect us to provide APIs that are simulation-centric, not data-centric. We also built for an existing ecosystem, so it's not just a one-off thing, one-off experiment. Our service had to fit in the production requirements of the game development, where a game developer could quickly train the AI iteratively as their game evolved. And so as you probably know, most research projects are centered around a core question and a hypothesis, which is really simple in concept, but requires a lot of innovation and pushing the envelope to make happen. For a real product, it's more about understanding the requirements and people who you are building for. And like with any problem with constraints, we broke it down and figured out solutions piece by piece, flexing the solutions as we went. So in this talk, I'll be breaking it down to high-level architecture. So how does a service work? Sharing game state. So how can a game developer share what's going on in their game? Learning to play the game. So tying the whole thing together by creating a process that works for game developers to train an AI that can play the game competently quickly. And finally, practical necessities. So some little stories about how we got feedback from game developers and built something just for them to make sure that our solutions works for them. And then we'll wrap it up with takeaways. And the order I present these and solutions that came with are really not chronologically happened. It didn't chronologically happen in real life, especially around sharing game state and learning to play the game. A lot of the decisions were made early to solidify the product experience while we continued exploration and added more features as we went. Cool, so let's first talk about high-level architecture. Where do all the action happen? The first thing that we had to solve for was our target games not running in our data centers, or even any data center at all. Game developers are quite cautious about where their game binaries are run on, and those locations are not guaranteed to have performant equipment. So the game could be run on the developer's machine, the game company's cloud VMs, game consoles, or mobile phones, all with varying capabilities. And the core requirement when an AI plays a game is that it must do so interactively. So the game state is provided as an input to the AI, and the AI calculates output actions that then feed into the game. And in order to play the game interactively, the process must happen within 33 milliseconds. And for an AI to learn to play the game, processing data and training the AI requires a substantial amount of computing power. So the intersection of these requirements meant that we only had a few ways we could solve the problem. So for example, training and running the AI on the game developer's machine would inevitably limit the quality of the AI due to computation requirements. Training is expensive depending on the magnitude of the data we train on and the algorithms used, because there's extensive mathematical operations that are happening on the data provided to generalize a multi-dimensional rule that the AI uses to make decisions. Whereas training and running the AI on the cloud and having the AI play the game through the public internet would lead to latency problems, and that hinders the synchronicity of the game state and AI actions. So running the AI just running the AI is not as computationally extensive because it's just a matter of taking the real-time data, running that through the rule that was created in the training step, and then acting on the results. But the game happens in real time, not as a human would play. So imagine the game state being shared across the internet, going to the cloud, the AI makes a decision, that decision coming back to the machine that's playing the game, and so on, back and forth. And imagine some network blips along the way. It's just not an accurate representation of how games are played, and we shouldn't be training on that inaccurate data to learn how to play that game. And we solved this problem by implementing the actor-learner pattern, which splits the AI into two parts: the actor which plays the game, and the learner, which figures out how to play the game. So the actor playing the game runs the AI, which takes input from the game and generates output to play the game. And then we place our actor in the client machine as an SDK. So SDK is a software development kit, which is integrated by the game developers into their game to share their game state and feed the actions from the AI into their game, while under the hood, it would communicate with our service, the learner. And to learn to play the game, the training the AI happens in the learner, where game data is processed through intensive mathematical computation to learn behaviors. And we placed our learner in the cloud, which could be scaled to multiple specialized cost-efficient machines hidden away from game developers. And as you can see in this diagram, the actor updates the on-device model to be better or try new things while continuously batching and sending data to learn from the gameplay happening in real time. And yeah, this is called the actor-learner pattern. It's a proven and well-known architecture in applied machine learning. And getting a little bit more detail, zooming in. So for the actor portion, we decided to use a set of tools called TensorFlow Lite or TF Lite. TF Lite prides itself on low latency, high performance, and a small binary size, all of which are important for running ML models on device with limited capabilities. So it made a lot of sense for us to try TF Lite for our actor portion. Our model would be generated on the learner side, transferred over via public internet to the machine running the game, where we unpack it and load the model to a model that can be run through TF Lite tools. And yeah, if you're interested in the details, you can look at the code in the open source project and learn about the real world application of tools like TF Lite. Cool, and another library we used was TF Agents, which is a library that wraps TensorFlow and allows us to define specs to train our model in agent-centric ways. So as you can see on the right side, we ended up using behavioral cloning agent for production AI, but we experimented with various RL algorithms. I won't go into too much detail here, but like a soft actor critic or proximal policy optimization agents. These are all RL algorithms. And TF Agents, the library, made it easy for us to swap in and out of these algorithms without having us to implement them. Cool, so with that, the actor-learner architecture allows our learner to train models from game data. But the question is, what is the game data that we send? What information do we send to the learner to train an AI effectively? So one idea that maybe a lot of people can come up with is game developers could just send raw pixel data for each frame of the game, like just screenshots, right? Well, machine learning researchers have done this repeatedly with old school Atari games to benchmark machine learning techniques, but the complexity of high resolution modern games makes it impractical to learn using this methodology. Hope that makes sense. On the other end of the spectrum, our service could ask game developers to directly define the data-centric features that they want the AI to learn from, representing them in data types required by machine learning libraries such as TensorFlow. Well, this would defeat our goal to make a service that is easy to use for game developers with no machine learning experience. So our solution was for game developers to provide data about their game through a game-centric API specifying first observations. So those are game state that the player sees at any given moment in time, like, oh, the enemy is there or the wall is here. And then actions, which are logical interactions that the player can perform, like walk left, jump, stuff like that. And then rewards are numerical values that tell the AI how well it's doing, like got 3 points or lost 2 points. So with the observations figured out, those 3 types figured out, our next challenge was defining observations for a service to efficiently learn the game from. So there are definitely many ways to describe a game, but we want the versions that are the most efficient to learn from so that training the AI takes the least amount of effort and time for game developers. So take a look at the picture on the right. Based on the game logic, how it's implemented in the code, it might be tempting to put the map of the world in observations. So like that, what I mean by that is like the yellow goal is at 7-2, the blue player is at 4-6. But what would a person playing the game say? Well, they would probably say, oh, there's a goal directly ahead of me 5 degrees to the left. So imagine, zooming into a first-person view. people would say, oh, there's a goal ahead of me, the yellow goal 5 degrees to the left. So what is more efficient to learn from? Turns out that the latter, where we're representing the game as a person would say, is more generalizable to learn from. So regardless of the different specific coordinates you may be at, the action is still the same. Keep walking ahead or keep steering to the left. So rather than learning multiple sets of situations and letting machine learning figure out that they all require the same action, it was much more effective to reduce that extra step and strip away details that don't directly contribute to the action you take and focus on the ones that do. And we named this technique Egocentric Observations, which is representing game state relative to the controlled entity. And we advised our game developers to observe game state that way, added APIs to help do those transformation automatically. So if game developers did want to share those 3D positions of different entities, like, you know, XYZ is the player, X plus one, Z is camera, goal, enemy, we do the pre-processing to map it to these egocentric observations. And here's another feature we built to represent game state, feelers. So feelers are basically raycasts around the player entity, detecting walls, enemies, floors, etc., and informs what is around the player in the game state. So raycasts, I guess, if some of you are probably not game developers, if you don't know, it's just like physical light rays to detect if something has hit something, if something has been observed. And we initially designed it to be able to distinguish the type of thing it hits, like, oh, that's an enemy right there, or wall right there, informing it to make its distinct actions. But we found that more information wasn't necessarily better. So all of the games we integrated with, we ended up using just reporting the distances of these feelers rather than, checking what type it was. So we would just say if it hit something or not and the distance. And we'd experiment with different coverage for the feelers, like 360 all around, or just looking forward, or how many feelers looking forward, all of those things. And behind the scenes, they become inputs to the convolutional neural networks. And let me explain what that means. So the feelers, as discussed in the last slide, are inputs to the convolutional layers, which you can see in the diagram as the orange box on the left. And the outputs from this are inputs to the fully connected multi-layer neural network, which is the gray big box. And the large number of inputs to the fully connected neural network increases training latency and degrades AI quality, especially on limited samples, which is not something we want. So like in the example I was saying with experimenting with lots of raycast feelers around the player, it would actually increase the training latency and lower AI quality, which is what we don't want. So we added additional pooling and padding layers. So pooling is technique to reduce output count, and padding to control the number of outputs to fix the CNN output size to be 4 for anything more than 4 feelers. So even if you have 360 all around with 30 feelers or something, it would be the outputs of the convolutional layer would be only 4. And as a result, our AI quality and training speed got better. And I also attached the link to the code that does this portion if you are curious. And yeah, such strategies to make learning more efficient with small, limited samples may be considered shortcuts in the academic world. They were really worthwhile to achieve our goals with limited samples and compute power. Right, so now that game developers could describe their game, we needed to provide them with an AI that can play their game. So reinforcement learning, where the AI learns to play a game autonomously through rewards and penalty signals, was initially the obvious choice, has been the go-to technique to train AI that plays games like AlphaStar for StarCraft and OpenAI 5 for Dota 2. After all, RL is basically how humans play games or do anything. We interact with the environment, get feedback, and keep trying things. The primary issue with RL for our requirements was that RL algorithms require order of more magnitudes, more data than our developers could provide, and also have unpredictable outcomes. For example, OpenAI 5 played 180 years of worth of games every day to learn to play Dota 2. Another non-trivial issue is that reward shaping, or defining rewards and punishments, is pretty tricky to get right, even for a machine learning expert. So this is like the lost 3 points, got 2 points. A bad reward or punishment can easily confuse the AI at training, and we found that time spent waiting for the AI to learn to play the game even to walk straight, for example, and exploring different sets of rewards to be really frustrating. So we would just sit there for hours looking at something that doesn't do anything. And it's not a good experience that we wanted our game developers to face. So instead, we found more success with a solution of learning by watching a human play rather than autonomously learning from reward signals. So we use the technique behavioral cloning, a method that applies supervised learning on state action pairs. Algorithmically, this is simpler than reinforcement learning in that we know the mapping of the desired state and action pairs and learn the pattern of it, rather than finding out if the state action pair was a good pair by getting punished or rewarded for it. And with this approach, game developers were able to generate AI that acted similarly to the demonstration behavior provided at training. So for example, someone could send 2 minutes of examples playing the game for a task, navigate to a goal while avoiding obstacles. And the AI would be trained that can do roughly the same for similar levels reliably. And as the AI plays the game, it gets stuck when it encounters a situation that it hasn't seen before. To solve this, we utilize a technique called human-in-the-loop training. In the human-in-the-loop training, the game developer would watch the AI play the game, and when it starts behaving incorrectly, they could jump in and provide a demonstration of what to do in such situation, which is a flow that was made possible by the interactive nature of games. The additional data helps train higher quality AI that can handle those similar situations in the future. And this is like a fun flow for game developers. They would provide demonstrations, watch the AI play, correct it, and then you can see the AI succeed in similar situations where it failed before, completely in real time and interactively. So this is roughly coined as continuous imitation learning, and it's known for its sample efficiency, which is exactly what we wanted. Well, unfortunately, pure behavioral cloning only tells us how good the model is at predicting the state action mapping, not how good the AI is at playing the game. So to find that out, we added an additional autonomous learning step that the game developer could trigger, step away from their desk for a few hours, and come back to see the AI playing the game at a higher competence. So here's what happens in this step. The AI autonomously interacts with the environment, gathering success and failure metrics to learn which version of itself is best at playing the game. So this takes the concept of RL, of making a decision based on a reward signal, but applies it at a different layer at model selection. And the final version of the AI can be then used to run tests and detect bugs in the game. So here's a rough flow of how using the service might look like. So first, you provide demonstration, which is really to say you play the game to demonstrate basic mechanics of the game. So like 2 rounds in a racetrack. Then you let the AI take over. So in this step, you have a status that you can read from the SDK to tell you if a training has completed on the data, all the data you have provided. So maybe you let it run until training completes, watch it play, see it make mistakes, correct them, watch it complete training, so on. Or you can even provide corrections before the training completes, because there will be draft versions of the model returned ready to play. So as you provide more data, we trigger more training that weighs all of the data equally. So eventually when all the training completes, we would have trained on all versions of the AI ready to evaluate. And for the training completion was determined by the learner to see if the behavioral cloning scores had not improved for 4 models or so. So this isn't accurate. How good is it at playing the game? It's more like, how is it good at detecting the state action mapping? So it's more of like a correct kind of check rather than is it actually playing the game? And once you see that the AI is pretty good at playing the game, the training phase is complete. And then you let it run on the evaluation mode where you had defined the success binary and the timeout and let the AI play the game autonomously while using versions of itself. So while you can step away from your desk and go home for the day. And when you come back in the next morning, the best version of the model has been decided and outputted. And now you can use this version to run future tests for multiplayer dev testing or whatever you might want. And there are various ways to do this flow. Like you can train some, take a snapshot, add more training, and then evaluate, go back to the training snapshot, do more training, and then do evaluation before getting to the last inference stage. And during inference, there's no training. It's just running the best model of itself that it determined. That's just what it's running. Cool. Right, so that was it for the general system and how we made it work. Now I'd like to share some stories about how we built features on demand as requests were made from game developers we worked with. Games, as with any time-tested software, is something that has been built through computer history fighting against lots of resource constraints. So it's really no surprise that game developers implement their own memory management system. That's to say they don't use whatever is provided by the language by default, but they have more control layers to cleverly optimize, like deallocate things prematurely or allocate and so on. Our SDK, which is something I haven't gotten too much into detail in this talk, is what the game developer integrate with to share their data with and run the AI. So it's a component that talks to our service. The SDK portion is the actor portion. We had a few options for this, and we went with a dynamic library for Windows C++ because we weren't comfortable with sharing the source code. The dynamic library meant that the SDK code is dynamically linked with the program code, and the objects created by the SDK are allocated by the SDK code separately from the application, so the game's objects. But this meant that objects that were passed across the API boundaries had some tricky things to deal with. So in the example on the right, this is brain.h, or one of the header functions in the SDK, which is compiled in the context of the game application. So when the brain ID is allocated through the function inside of the SDK, thus using the SDK allocator, it would be returned to the application or the game code to deallocate, which doesn't have the same information as the SDK allocator. So basically, the application deallocator would be assuming, based on their memory management, that they can simply deallocate the object based on their information, the information they have, but instead reads garbage at the expected location and then crashes the program. We don't want crashes while running games with our SDK, obviously. So after we encountered these issues, the debugging with game developers, we decided we needed to implement an emergency feature. So I implemented a global allocate free override function. So basically, the game developer defines their own allocation functions, which reports to their memory management system and passes that through our set API, which then sets those custom functions as callbacks to the global generic delete and new functions. So I won't go into too much grilling detail here, but you can see the allocator code that's in our open source project that's linked below if you're interested. And with this feature fully integrated with a game that used a custom memory management system, we were able to run the game without any crashes, which is totally crucial for getting anything working. So moving on to another feature request. With our early access partners, we had basically white glove support, which is to say that we held their hand through the whole process. They wrote the code, but we met with them almost every day for the initial months and debugged their AI with them. But that's not really sustainable or scalable if you're building a tool for game developers to work with on their own. Plus, there was, with COVID, there was a lot of time difference for a lot of these game teams and us. And over video, we didn't want to sit for hours on video conferencing and work through problems with them. So for any tool, any service you're building, it's good to have tooling to support your customers. Here's a screenshot of our debug visualization tool. The goal is to double check the data that they sent to our service and that to be available to the game developers. Like if they've defined observations that they thought it was correct, but turned out there was a bug on their side that caused our AI to get confused. So you can see stuff like distance to objective. So that's like the distance of the player to the objective. Number go up and down, as well as the scene view on the right, which is showing what was detected by the feelers. And there are real concrete examples of issues we discovered through this tool. So one was invisible geometry or fake geometry seen by feelers. So for example, in navigation, feelers detect the distances of what is around the player. And that's really important for learning navigation. One time there was an object in the map that was not detected by humans, but detected by the detection code, which shaped the way the AI played the game because they'd always avoid that spot. And we're like, why is it avoiding that spot? Well, turns out there was a object, like a cube or something, that was just clear and transparent and not seen by the actual humans. Another one, expert player making decisions based on information that the agent can't see. So when you train an AI to play the game, it's really important to know that they can only learn from what you send them. So like something like sound, oh, here are footsteps, I gotta run away. Like if you're not sending that data that there's footsteps, then you shouldn't be playing the game based on those footsteps that you hear. You should probably not listen to those. So this tool was a good reminder of what data our service actually got to learn from, rather than what the player can see or hear. Another one was actions not plugged in correctly. So say you were like, jump, 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 jump across the time of some episode, and you're like, oh, I think I jumped then. And then you can check back on the timeline view and see, is the jump Boolean on at all of those times, and double check, sanity check your implementation. Another issue we encountered was transform issues. So in one of our partners' games, their z-axis was our y-axis, which messed up our egocentric observations feature, the feature that I talked about that mapped the 3D view into egocentric observations. And we were able to detect this issue using the scene view. So needless to say, this tool helped out a ton, and we built it ourselves. Yeah, and so basically what I take away from this is that building a real-world product means prioritizing real-world problems. Oftentimes, we have to know what's going on before improving the AI quality, and the custom allocator made it possible to move past the step of having your SDK work with a real game and not crash, and the debug tool made sure that companies can rapidly iterate with minimum support from our side. Cool, so let's recap on everything we covered today. Building a machine learning service can be intimidating with the sheer velocity of research in the field, especially when real-world requirements diverge from academic assumptions. We had the unique constraints of not having access to the game binary, needing to make the tool work for game developers with no ML experience, and actually training the AI to play the game in a way that works with the game development workflow. To solve these, we utilized proven techniques such as continuous imitation learning, being very sample efficient, took what might be considered shortcuts in academia, like egocentric observations, and applied basic principles in different layers, like the evaluation model selection mode, which was heavily inspired by RL. To build a product for a real audience, you can't just simply copy what a research paper has done. You really have to pick and choose different techniques at sometimes unexpected layers to accomplish an ideal experience for your audience. And finally, let's not forget that a real product needs to work for real customers. So it requires you to build what's necessary to make it work with those real customers. Thank you so much for attending this talk. And if you'd like to learn more, here are the links below to find out more about this project. The open source project is a simplified representative of what we build with most of the functionalities in the early access program. And the blog post covers some of the concepts I covered in this talk and the others that I didn't. Cool, I will take any questions that you may have now. Thank you so much. Should I stop? Okay.
Hello. Hi, Hina. How are you? Thank you so much for your talk. I learned so much, so much about game dev with AI there, and I'm very thankful for you sharing your knowledge. And I can see that our audience here are giving you loads of claps and saying thank you. So I do see that there is one question here we have in Q&A. Again, if anyone has any more questions, please ask in the Q&A tab. So the question we have here is the example, hold on, the first one, is it useful to use different models with differing levels of training just to see what happens? Or is it best to use the best model all of the time?
Sorry, I'm gonna just bring the screen over. Is it useful to use different models with different levels of training to just see, oh, okay, I see. So like, for example, like we have data that gets sent to the service to learn from. So maybe, for example, like just the first part or just the like the sampling of the data to train from. Maybe some does it, oh, like for different, sorry, I'm kind of confused about just to see what happens. So you want to see, so maybe they're referring to like the evaluation mode where we try a few different models to see which one's the best. So the reason why we did that was because we don't know which model is the best. So we just simply let it run, and the game developer can see the different models trying out things in the environment. And the way you find out which is the best model is based on if they're succeeding at the tasks in the game. So at the end of the day, is it best to use the best model all of the time? I think it depends on the task and the task complexity. So for example, a racetrack, you have a racetrack that you have a model that completes the racetrack, and then you have a model that does really poorly on this racetrack but goes wonky all over. Well, there's different goals for this. So for example, detecting bugs in a game where you want to see if there's any holes in the map, for example, then you want some erratic behavior that doesn't necessarily complete the racetrack course every time, but then actually does really poorly, gets stuck, all these things, but eventually covers all the ground. Then that model is probably the best for your purpose. And you would probably train the models to be getting those samples so that they behave similarly to that. So for our purposes, we were really focused on training the AI to play the game competently, which meant that they would finish the course properly, or shoot all the enemies and proceed to the next level. So it ended up that we focused on doing using the best model all of the time. But I think there's also different use cases where it might make sense to do different levels of training. And by different levels of training, I think that's another nuance where you could train with a lot of data or just a little bit of data. And oftentimes, we had a little graph of like how much better the AI got at playing the game over time. And it's usually like there's a sweet spot. And I didn't go into this at all, but if you train too much, it's like doesn't get better after a while. So that's what I'll say for the different levels of training. Yeah. And then I guess there are two other questions.
Yeah, the next question we have here is, the example works with Unity 3D projects, but what about Unity 2D projects?
Right, yeah, so absolutely. Unity 2D projects have the same thing, right? So if you're thinking like a 2D game where it's like a platformer, for example, where, jump, see forward, those kind of things, it's even more simple, and it's actually easier to learn from than 3D games because there's less things to learn. It's only 2 dimensions that we have to learn. So yeah, it works for 2D. You wouldn't be using feelers in the same way. You wouldn't be using egocentric observations in the same way, but it's even a simpler version. So using the ground level API of observations, you would say, distance to objective. Like if your goal is just to go straight to the objective, it's really just minimizing that. That's what you're learning, is minimizing that distance to the objective. So, and then if you have obstacles, for example, it's like, if there's things you need to jump over, you can detect that as well. I'm just trying to how, in front of me, there's a block. That's something that you can observe. And then based on that, you jump. And that will be linked by the AI. So there's nothing really different about 3D and 2D. You can actually train the 2D one probably easier because there's fewer things to keep track of.
Awesome, thank you. And then the next question here we have Alexandra said, this is cool. This is too cool. What did you wish you would have done differently in the project?
Thank you so much. It's really great to hear that people thought this was cool. I thought it was pretty cool too. What do I wish I could have done differently in this project? I took a lot away from just being a software engineer and how to become a better software engineer during this project. And I think I was a little bit too focused on getting things working in a way that's like more simplistic, without really understanding the background of it sometimes. So I wish, and I learned this gradually, is to just take one step at a time, really take time to learn rather than making sure to accomplish, which to be fair, this project was, like a startup within Google, so it made sense for us to move fast. But I wish I had taken advantage of all the resources I had. I worked with ML experts. I was not an ML expert at the time. I didn't work with ML before this, so I wish I had taken the opportunity to learn more and read and enjoy that process rather than enjoying, the results. So I think there's a lot I learned about enjoying the process and enjoying the journey rather than enjoying the results. And as for the project itself, we published the open source project and the blog post, and I think I do wish that there were more findings that we could have had about, specifically, we did hyperparameter tuning. I was driving a hyperparameter tuning part of this project where basically we were trying to optimize which set of hyperparameters work for different which were like the sweet spot to train on to give a really good AI. So we didn't end up publishing those findings. So I wish we we found more things about it and was able to share about it. But yeah, I think that answers the question.
Thank you. And that's all the questions we have in here. If anyone has any last questions, please ask. But otherwise, I hope everyone has a fantastic rest of the day at Connect. And yeah, I just want to thank you, Hina, so much for sharing your knowledge with everyone here. And I definitely learned a lot about game dev with AI because I didn't know too much about it before. So a massive thank you very much. And the recording of this session will be available on YouTube in a few weeks' time. And also, yeah, thank you for all of our attendees that joined us today as well. We hope you enjoy the rest of your day. And you can check out the networking feature on the left-hand side if you want to connect with people today. It's awesome. That's one thing I love so much about Connect on Hopin, because you can connect with anyone across the world, and you get about 3 minutes to speak to someone and connect with them. So yeah, it's really cool. I met a lot of people through that. And also you can check out the expo booths to connect with all of our amazing sponsors. So yeah, I hope everyone enjoys the rest of their Connect Forward. And again, thank you very much, Hina.
Thank you. Thank you so much. Thanks everyone for this opportunity. Thank you. All right. Bye. Bye.
Bye. See you. Bye. Have a lovely day.